Hello everyone, I am Sukant Vats, Assistant Professor in Department of ICT at Tecnia Institute of Advanced Studies. Today we are starting the video lecture series for the course Data Structures and Algorithms. The topic that we will be discussing in today's session are Introduction of Data Structures and Algorithms and Attributes. Welcome to this session on the Introduction to Data Structure and Algorithms, often abbreviated as DSA. Whether you are a beginner in programming or someone looking to strengthen your foundational knowledge, this session will help you understand what DSA is, why it is important, and how it forms the backbone of computer science and software development. What is DSA? Let us start with the basics. Data structure are ways to organize and store data in a computer so that it can be used efficiently. Think of them as containers that hold data in a specific format, allowing for easy access, modification, and management. Examples include arrays, linked lists, stacks, queues, trees, graphs, and hash tables. Algorithms are step-by-step procedures or formulas for solving problems. They are like recipes that tell you how to perform a specific task, such as sorting a list of numbers, searching for an item, or finding the shortest path between 2 points. Together, data structures and algorithms work hand in hand to solve real-world problems efficiently. Data structures provide the foundation, and algorithms are the processes that manipulate the data stored in these structures. Why is DSA important? Now you might be wondering, why should I learn DSA? Here are a few reasons. First, efficiency. DSA helps you write efficient and optimized code. For example, choosing the right data structure or algorithms can reduce the time and memory requirement to solve a problem. Second, problem solving skills. DSA teaches you how to break down complex problems into smaller, manageable parts and develop logical solutions. Third one, interview preparation. DSA is a core component of technical interviews for software engineering roles. Companies like Google, Amazon, and Microsoft often test candidates on their DSA knowledge. Fourth, foundation for advanced topic. DSA is the foundation for more advanced topics in computer science such as machine learning, artificial intelligence, and database management. Now, key concepts in DSA. Let us briefly touch on some key concepts you will encounter in DSA. First, time complexity. This measures how the runtime of an algorithm increases as the input size grows. It is often expressed using big order of notation, example order of n, order of log n. Now the second one is the space complexity. This measures the amount of memory an algorithm uses relatively to the input size. Third one, basic data structures, arrays, linked lists, stacks, queues, and hash tables. Fourth one, advanced data structures, trees, binary trees, AVL trees, graphs, and heaps. Fifth one, common algorithms, sorting, example bubble sort, merge sort, searching, example binary search, and graph algorithms, example Dijkstra's algorithm. How to learn DSA? Learning DSA can seem overwhelming at first, but here are some tips to get started. First one, starts with the basics. Begin with simple data structure like arrays and linked lists, and basic algorithms like linear search and bubble sort. Second, practice regularly. Use platforms like LeetCode, HackerRank, or Code Forces to solve problems and apply what you have learned. Third, understand and do not memorize. Focus on understanding the underlying concepts rather than memorizing codes. Fourth one, visualize. Use data structure and visual tools to understand how data structure and algorithm work. Fifth one, build projects. Apply DSA concepts in real world projects to see their practical applications. Real world application of DSA. DSA is not just theoretical, it is used everywhere in the real world. Here are few examples. First one, search engines. Algorithms like PageRank used by Google rely on graph data structures to rank web pages. Second, social media. Friend suggestions on Facebook or Instagram use graph algorithms. Third one, navigation apps. Apps like Google Map use shortest path algorithm like Dijkstra's algorithm to find the fastest route. Fourth one, e-commerce product recommendations on Amazon use data structures like trees and graphs to analyze user behavior. Now we are going to start with the first topic of data structures and algorithm, that is attributes. What are attributes? In the context of data structures, attributes are characteristics or properties that define the structure or element of the data being represented. These attributes allow us to perform operations on the data and interact with it more effectively. For example, if we have a linked list, the attributes might include data, the value stored in a particular node, next pointer, a reference to the next node in the list. In algorithms, attributes refer to properties or parameters that influence how the algorithm behaves or performs. These could include the number of operations or comparisons the algorithm makes, the structure of the input data. Let's break down attributes in different data structures. Attributes in data structures. Arrays. Array is a collection of elements, all of which are of same type, stored in a contiguous memory locations. The key attributes of an array include size or length, the number of elements that the array can hold, index, the position of each element within the array, usually starting at 0 in most programming languages. Next one is capacity, the maximum number of elements that can stored in the language like C or C++. Now discussed on linked list. A linked list is a linear data structure where each element node contain data and a reference or link to the next node in the sequence. The attributes include head, a reference to the first node in the list, tail, a reference to the last node in the list in some variations. Next oblique previous pointers. In singly linked list, it refers to the next node, while in doubly linked list, there are both next and previous pointers. Now let's discuss on trees. In trees, each element node store data and references to child node. Key attributes include root, the topmost node from which all other nodes can be traced, height, the length of the longest path from the root to a leaf node, depth, the distance from the root to the current node. For example, in a binary search tree, BST, we might have left child, the left subtree of a node, right child, the right subtree of a node. In graphs, graphs are more complex structures made of nodes, that is vertices, connected by edges. The key attributes in graphs are vertices, that is the entities connected in the graph, edges, the connection between nodes. These could be directed or undirected. Weight. a numerical value that might be associated with an as inverted graph. Now we discuss on stacks and queues. Stacked, a linear structure that follows the last in, first out, that is LIFO principle. The attributes of a stack include top, a reference to the topmost element, size, the number of elements currently in the stack, queue, a linear structure that follows the first in, first out, that is FIFO principle. The attributes of a queue include front, the first element in the queue, rear, the last element in the queue. Third one is algorithm attributes. In context of algorithms, attribute influence the performance, complexity and efficiency of an algorithm. Some common algorithmic attributes include time complexity is the amount of time an algorithm takes to complete as a function of the size of the input. It helps determine how scalable an algorithm is. For example, order of n, linear time complexity where n is the input size. Order of log n, logarithmic time complexity often seen in algorithms like binary search. Order of n square, quadratic time complexity seen in algorithms like bubble sort. Now discuss on space complexity. Space complexity is the amount of memory an algorithm uses relative to the input size. Like time complexity, it helps us understand how well an algorithm can scale in terms of memory usage. Stability. For storing algorithms, stability refers to whether or not equal elements retain their relative order after sorting. For example, stable sorting. It includes bubble sort, merge sort. Unstable sorting. It includes quick sort. Correctness. An algorithm is correct if it produces the right output for every possible input. For example, in searching algorithms, the algorithm must return the correct index or value or indicate if an element does not exist. Fourth, practical use of attributes. Attributes are not only important for understanding data structure theoretically, but it also for optimizing them in practical scenarios. Let us consider the following examples. Optimizing search operations. When dealing with large data sets, choosing the right data structure based on its attributes can drastically reduce time complexity. For example, arrays. Arrays are great for fast access when you know the index, but insertion or deletion is slow. Linked list allows for faster insertion oblique deletion, but are slower for direct access. Choosing algorithm based on space and time complexity depending on the problem at hand. You may choose an algorithm based on its time or space complexity. For instance, merge sort. Merge sort is often preferred over quick sort for large data sets despite its high complexity because it guarantees order of n log n performance even in the worst case. Breadth first search (BFS) might be used over depth first search (DFS) depending on whether the solution lies closer to the root or deep within the graph. Conclusion. To sum up, data structures and algorithms are essential tools for any programmer or computer scientist. They help you write efficient, scalable, and optimized code while improving your problem solving skills. Whether you are preparing for interviews, building software, or exploring advanced topics, a strong foundation in DSA will always be beneficial. I hope you like today's session. Please do like, subscribe, share Tecnia TV.